Okay, very good. So just a brief recap of the topic at the end of the last lecture. So last lecture we discussed a procedure to extend the ADM phase space and to a new phase space, which is of course larger than ADM. So we use a variable KAI, which is extrinsic curvature, and EAI, and what we call densitized triad, equals to square root determine Q and EAI, and this EAI is the triad or the basis, also normal basis in 3 dimensions. And using this variable, we get the canonical Poisson bracket between EAI x and KJB y equals to delta function. But in our convention, there is a prefactor kappa divided by 2, delta ij, delta ji, delta ab, delta 3 x and y. Okay, and the Poisson bracket between E and E equals to Poisson bracket between K and K equals to 0. Okay, so it means that these new variable E and K, they are conjugate pairs of our phase space, right? And also I mentioned that by what we call enlarging the phase space is that we introduce some additional gauge degree of freedom. Namely, you can consider gauge transformation. I transform to lambda. What I used is O ij. Let me see. O ij. No, right now it's not exactly O ij. Yeah. Okay. Yeah, it's the same. So. No, it's not exactly the same. So let me introduce. This is not. So this O will be the O inverse last time. So well, let me. So that therefore let me call it Mij and Ej and Kjb transform to Ib Ij. Yeah, so this is this M matrix M belongs to the SO3 group, which means that it's a 3-dimensional rotation group, and it just rotates. It's a linear transformation and rotates this triad. Yeah. And similar at the same time, it rotates the K. And you can see that this is Ij index. So this this matrix has Ij index acting on the Ij index of EAI and KIB, right? And so you can view, if you learn a little bit about gauge theory, you can view this Ij index. There are actually some flavor index of the gauge theory. Yeah, it's similar. Let me at this moment, let's say it's analog of the flavor index in the gauge theory. Okay. Okay, and also I have shown you that given this conjugate pair K EAI and KIB, and you can determine the ADM variable QAB and PAB. Yeah, but the inverse is not true because you have a gauge degree of freedom. So if you can determine, so another word to say is that you can determine EAI and E and K variable from ADM variable, but up to a SO3 rotation. So this is the statement. Okay, but you can determine uniquely the ADM variable from E and K. So that's the property of this EK variable. That's why we say we have extended ADM phase space. Extended ADM phase space. Okay. Now, since we have experience that usually gauge transformation relates to constraint, right? So then there must be a constraint which can generate these this SO3 gauge transformation. And indeed, and we have a constraint, and I have mentioned that constraint last time as well. So we just need to translate, well, write precisely the expression for the constraint. And this constraint is what we call Gauss constraint. Gauss constraint. So it's a name. This name indicates it's kind of analog of Gauss's law. But at present, you are not able to see it is analog of the Gauss's law. But in a moment you will see that it is indeed analog of Gauss's law. So now this Gauss constraint I will call Gj. It is given by epsilon JKL KKA EAL. Okay, and so here AA are contracted and KL are summed with epsilon JKL. Okay, so you can plug in the definition of density hydride plus the definition of E. So you find that this is just a determinant Q epsilon JKL KKA EAL. Okay, and you find this is just a well KKL, right? Because this is like contracting A. It's like expanding. You extract the coefficients of K at the basis EAL, right? So this part it is just KKL. Yeah, I'm here because the KL index is raised up and lowering by using delta ij. Yeah, so you are free to move up and down. Yeah, so it's just the KKL, but KKL being a K being a symmetric tensor. Yeah, so KKL is a symmetric matrix, and when you contract with epsilon, definitely you get 0. Okay, so this is clearly a constraint in this new variable K and E, because clearly it is constrained because it has no time derivative. Yeah, so this Gj equals to 0. This equation has no time derivative, so it's just a constraint, constraining your variable at on each spatial slice. Okay, and then for the Gauss constraint, this is defined locally at every point. You can of course define the smeared constraint. Smeared constraint. So what I call G lambda equals to T3x Gj x lambda j x. So this lambda, you can view this is just a vector with index j. Okay. This vector, well, or you can view this is just a three functions. J equals 1, 2, and 3. Okay, just the 3 functions. Okay, so now the next thing it is your homework. It is easy to check that you can consider the gauge transformation generated by this constraint. Yeah, similar as we have done for ADM variable, but now we just have a new constraint. You consider this boson bracket. EA phi. Yeah, so this is, as I mentioned before, this is called the infinitesimal Hamiltonian flow generated by the function, generated by this phase-space function, generated by this phase-space function, which is a constraint. And then this is supposed to generate a gauge transformation because G is a constraint. So you can do this is the definition. Yeah. And the homework is that I want you to show that delta lambda is the infinitesimal gauge transformation. Gauge transformation, yeah, basically this gauge transformation. So they are infinitesimal version of this gauge transformation. J K A transforms to Mij K J A, right? Okay. So I mean, you have to to work it out. You have to understand what is exactly what I mean by infinitesimal version of this gauge transformation. So these are the finite version of the gauge transformation. But of course, you have to work out the infinitesimal version of this gauge transformation. It should be very easy, and then to compare with these gauge transformation generated by the constraint. Okay, and all right. So I probably I should mention once again, but I have mentioned that many times last time. So the reason why we call it gauge transformation, it is because it is the rotation of the variable E and K, but leaving the ADM variable invariant. Yeah, that's the reason why we call it is a gauge transformation, because it leaves the physics invariant. The physics is determined by metric. So here this E and K is some enlarged phase space variable, extended phase space variable, and it includes some gauge transformation and leaving the ADM variable invariant, but rotates E and K. Okay, and we find those gauge transformations are generated by the constraint. So this constraint is also satisfied automatically by those EK variable. Yeah, as we have seen here. As we have seen here, it equals to 0 automatically, right? And that's why you automatically get a constraint, and you also automatically get a gauge transformations by passing from ADM variable to the extended phase space variable E and K. And here, this homework just let you work out that this constraint and gauge transformation are actually related. So the gauge transformation is generated by the constraint. Namely, the Gauss constraint Tj generates this SO3 gauge transformation. So here, the matrix M belongs to SO3 is the three-dimensional rotation group, the rotation matrix. So I mean, being M belongs to SO3, it means that delta Ij, Ij, delta Ik, and KL equals to delta JL. Yeah, and also determine M equal to 1. So these two equations means that M is SO3. All right. Okay. So and you can also draw a picture and the relation between the extended phase space and ADM phase space. Relation to ADM phase space. So this is your extended phase space given by K and E, right? And now, firstly, you have a constraint surface. You have a constraint surface, and you have this G. This is constraint surface G J equals to 0. Yeah, this is your constraint surface. But at the same time, you have also the gauge orbit. Yeah, generated by constraint. Yeah, generated by constraint. right? And moreover, what you can see that the constraint is gauge invariant. Yeah, you see. So this constraint is just all the indices are contracted. KL are contracted, AA are contracted, and the rotation of JKL only rotates the constraint. So because the constraint has the index J. Okay, so under the gauge transformation, okay, so the gauge transformation, SO3 gauge transformation transforms GJ just to MIJ DI, something like that. Yeah, and here M belongs to SO3. Okay, so it means that this gauge transformation transforms Gauss constraint to a linear combination of Gauss constraints. Yeah, so it means that it leaves the constraint surface invariant. So because constraint surface Gj equals to 0, and after gauge transformation you still get 0. So this is so Gj equals to 0, and you still transform to how to write, still transform to 0. Yeah, so it leave constraint surface invariant. So constraint surface invariant. Okay, so it means that the gauge orbit is running along the constraint surface. Yeah. So these are the gauge orbits. Okay, so now you can do some similar things by taking the quotient. So you can consider the SO3 gauge invariant quantities, and they are just the functions of gauge orbits. Yeah, they are not a function of the constraint surface, but actually functions of gauge orbit. Namely, they are constant along gauge orbit. So they can be defined on a certain kind of reduced phase space. So you can consider each gauge orbit is just a point, yeah, on the on some kind of reduced phase space. This is not a full reduced phase space, because here you only reduce with respect to the SO3 gauge transformation and Gauss constraint, right? And this is, but still you can consider quotient space, and this quotient space is precisely the ADM phase space. Yeah, because here you are having a constraint surface satisfying Gauss constraint, and then you remove the you quotient with respect to SO3 gauge orbit. So these are SO3 gauge orbit, and you remove SO3 gauge orbits, and the after removing the gauge redundancy, what you are left is just the ADM variables, and because only difference between EK and ADM variable is Gauss constraint and SO3 gauge transformation. Okay, and so that's the reason why the quotient space is just ADM phase space. So here, this picture basically summarizes the relation between the extended phase space and ADM phase space. Okay. Okay, so with the preparation of this extended phase space, we can take a further canonical transformation to the so-called Ashtekar variable. Ashtekar new variable. Okay, so these are the variables we often use for the quantum theory. Okay, so this is, as I said, there is a so-called canonical transformation. Yeah, so what is the canonical transformation? Canonical transformation, you can view, firstly, it is a coordinate transformation in phase space. So, or you can view, firstly, a priori just a change of variables. Coordinate transformation in phase space. So what is this coordinate transformation? So here, from the canonical coordinate, canonical variable k I a, you transform to another variable. So e is going to be preserved, but you are going to introduce another variable ai. Yeah. And so I'm going to just give you some formula for IA, for this AIA. This AIA is linearly dependent on K. So the transformation between K and A is linear, but it has another term, what I call gamma. I will explain what it is. So AIA is gamma plus beta times KIA. So this KIA is the same KIA here. And so this AIA is called a Ashtekar-Barbero connection. Ashtekar-Barbero connection. So it is a connection field with gauge group SO3 or SU2. So it is connection, or it is, you can, so at the moment you are not able to see it, but in the end I will show you that this guy is a gauge potential, or it's a connection, or we call gauge potential. With a gauge group SU, yeah, let's call it SU2. Yeah. Because the relation between SO3 and SU2 is just double cover, and their Lie algebra is the same. All right, so later on I will show you. So this AAI is really a gauge potential. This beta, this coefficient of k beta, this is called a Barbero image parameter. This is a free parameter in the classical theory. So this parameter introduced firstly by these two guys. Barbero image parameter. Okay, and this gamma. So at the moment, I'm going to introduce this gamma in the moment. This gamma is a spin connector. It's called a spin connection one form, but I'm going to introduce it in 1 minute. Okay, and so I'm being so firstly it is just a coordinate transformation, yeah, but also it is also a canonical transformation. It is a canonical transformation. Canonical transformation. So what we mean by canonical transformation is that, so I think you may have learned what is canonical transformation in your classical mechanics. So being a canonical transformation, it transforms conjugate pairs to conjugate pairs. Yeah. So because E and K, it is a conjugate pair in the phase space. So after the transformation, this E and A must be also conjugate pairs in the phase space as well. Yeah. So it means that EIA and EAI are canonical conjugate variables. Canonical conjugate. Variable. Well, it is not completely precise. Well, it's E and A, they are canonical conjugate up to a coefficient beta. So more precisely, this canonical transformation is E divided by beta. and here is E divided by beta. So this is 100% precise. So here it means that the Poisson bracket of between E and A is as following. Is as follows. So I X and AJB Y equals to half kappa beta delta IJ delta IJB delta 3 and so on. Okay, so here you can see that if you remove this beta on the right hand side to left hand side, you find E divided by beta is really canonical conjugate to A. Well, it's the same formula as well as here. It's the same formula as here, right? And but you just replace K by A, yeah. Right, and so E and A, they are canonical conjugate variable, and also this Poisson bracket and the Poisson bracket between E and K, they are the same Poisson bracket. Yeah. So and what we call this is a canonical transformation is that we keep Poisson bracket, we keep the definition of Poisson bracket invariant, but just making a coordinate transformation or change of variable in phase space, but still we end up canonical conjugate variables. Yeah. So it means that we keep phase space invariant, we keep Poisson bracket invariant, but we change the variable from EK to EA. But before the transformation EK, they are canonical conjugate, and after the coordinate transformation, this EA is also canonical conjugate. Yeah. So that's the point. So which means so this Poisson bracket has to be derived from previous Poisson bracket. Okay, and at the same time, E equals to AA Poisson bracket equals to 0. Okay, so this means that E and A Poisson bracket, E and A, they are really canonical conjugate variable. So and then you can equivalently write. So this is a result. This is not a. This is the result derived from EK Poisson bracket. So we can write Poisson bracket equivalently. Yes. And we can equivalently write Poisson bracket in terms of E and A variable. Before it was written in terms of EK variable. But since it is canonical transformation, you can write in terms of EA variable. So here you have to be a little bit careful. Is that the coefficients on the right hand side for E and A, it is kappa times beta divided by half. Before it was before it was just a kappa. Okay. So well, in order to prove this theorem, you have to know what is this gamma. So this is something I'm going to introduce right now. So what is gamma? This is gamma IA. Well, this is called a spin connection one form. Yeah, it is clearly a one form because you have an abstract index A downstairs. Yeah. And so here I'm going to just give you the definition of this spin connection one form. So it satisfies this equation. This one form is determined by this equation. Satisfying this equation. dA EJB. So this dA is just the covariant derivative compatible with the metric. Yeah. So this dA. So well, what is this dA? This dA is just firstly partial A EJB minus gamma CAB. Gamma is just the Christopher symbol. Maybe because AB is abstract index and gamma, as I said before, gamma is being crystal symbol. It is just it's not a tensor. It's just a bunch of coefficients, just bunch of crystal symbols. But still, I using CAB, so it means that in this formula, I'm just using A and B to be component index. Yeah, it's not really in this formula. It's not really abstract index anymore. But because I'm running out the index and the spatial component index supposed to be I and J, but now I use I and J already. So I don't want to use other. So I don't have other alphabet to use. So I have to use A and B. So which means in this formula you just consider A and B as usual component index instead of abstract index. A, E, L, B. Okay, so you see that and this guy equals to 0. So here you can view this is also a definition of this covariant derivative dA. Okay, but you can see that this is like covariant derivative act on a dual vector. If you view this J just for example 1, 2, and 3. So if you understand this covariant in that way, this is just covariant derivative act on a dual vector, then you only should have 2 terms. But here we add another term here. Well, the point of view of that term is that you view that this covariant derivative is also covariant with respect to this J index. Yeah, because as I said, if you have learned gauge theory before, you view this IJ index is just some kind of flavor index in gauge theory. So your covariant derivative is better covariant with that index as well. So which means that you can view this is a new definition of the covariant derivative, which is covariant in both AB index and also J index. Yeah. So which means so remember, I mean, when we talk about covariant derivative, it's covariant with respect to gauge transformation. Yeah. And AB, you have the gauge transformation, which is the diffeomorphism coordinate transformation. But you also have additional gauge transformation with respect to IJ, which is this ISO3 gauge transformation. So which means you have another sense of gauge transformation. Yeah. So that's why you have to better use a covariant derivative, which is covariant in the other gauge transformation as well. And that's the idea of defining this covariant derivative. This is covariant covariant derivative with respect to covariant derivative with respect to both both indices. This is A and J. Okay. Yeah. So this A, you can view this is, I mean, in the language of the gauge theory, you can view this A is some flavor index with respect to the diffeomorphism group. Yeah. And J is some flavor index with respect to the ISO3 group. Yeah. And I think most of you have taken my quantum field theory class, so you should have learned what we mean by the flavor index. And if you don't remember, just to review that. And otherwise, for other people, if you are not familiar with gauge theory and you could just take it as a definition of this quantity gamma. Yeah, it's just you can see it's just a linear equation equals to 0, right? And from that equation, you can solve gamma. So you can solve that epsilon jkl gamma ka equals to minus EBL. Okay, so then you can just view this formula is a well, it's a definition of gamma. Okay, and or this formula is the definition of this gamma gamma IA, yeah, spin connection one form. Yeah, and you can just apply this definition into the definition of Ashtekar-Barbero connection, and then you get the explicit formula. Also, you may wonder, because if you want to compute this Poisson bracket, you need a formula of gamma or of A in terms of K and A, or in terms of old variable K and E. Yeah. So here you can see it's explicitly dependent on K, but it also you need to find the dependence on E variable. So it's actually this gamma IA is a here this gamma IA is a function of E only. Yeah. But in this formula, I only see that it's dependent on small e, the